Good afternoon, students. In the last class, we discussed about the half-wave rectifier, right? So, due to some technical problem, it ended to the half-wave rectifier. So, today we will discuss full-wave rectifier. So, similar experimental setup is constructed here. So, considering one transformer, so it has primary coil denoted by P. So, and one secondary coil denoted by S, right? So this secondary coil of the transformer is connected to the two PN junction diodes, right? So calling this one as D1, and here one more diode. This is D2. So here it is PN, PN. Right now, from centrally tapped, we connected the load resistance. So across this resistance, we are going to take the output. So right, calling this one as RN. So across this resistance, we are going to take the output. Right. So now the primary coil of the transformer is connected to the AC source. So giving input voltage, that is V, here is time. So this one is the input voltage, right? So now what happens here is during the positive half cycle, that means during this positive half cycle, as it enters to the secondary coil of the transformer, right? So what happens? This P terminal becomes positive and N terminal becomes negative. Then the diode D1 acts as forward bias. That means during positive half cycle, D1 acts as forward biased. So D1 is acts as the forward bias. So it acts as forward bias means it allows the current which is passing in the external circuit like this, right? So here we are getting the output voltage. So from this, if we plot the output, so here we have voltage, that is output. Here we have the time t, right? So as the positive half cycle is passing through the diode D1, which is forward bias, then it allows the current, then we getting the output voltage. Then if we return the output voltage, we getting the pulsating voltage like this, right? So this is during the positive half cycle. So during positive half cycle, so here D2 becomes, so this P becomes positive, and here it becomes negative, and N terminals becomes positive. That means the diode D2 is reverse bias, right? So during positive half cycle, D2 is reverse bias. So for this reverse bias, there is no flow of the current in the external circuit. That means here the load resistance at the output we getting V is equals to 0. So here from D1 we are getting the voltage V, and from D2 we are getting the voltage 0. Then final voltage we are getting is V, right? So similarly during negative half cycle, right? So this one is the negative voltage, right? So during negative half cycle, so during negative half cycle, this P terminals becomes minus and N terminals becomes plus. So that means D1 behaves as the forward bias. That means D1 is reverse biased So then here P becomes plus and N becomes minus. So that means D2 is forward bias. So as D1 is reverse biased, it will not flow the current in the external circuit. That means it blocks the current which is flowing in the external circuit, right? So here we are getting the current I is equals to 0. So as D2 is forward biased, it allows the current which is to flow in the external circuit. So this will be flowing and it will reach us the load resistance, or then from here we are getting the output voltage when D2 is forward biased. That is, during negative half cycle also we are getting the voltage which is positive, right? So for that again we getting the voltage like this. So this is during positive half cycle and this is during the negative half cycle. That means here D1 is forward biased. So here D2 is forward bias. So this will continue for all the waves. Again, for the next one is for the positive half cycle and again for the negative half cycle. So here we getting the output voltage. So this is also we are getting this voltage as pulsating voltage. Right? So that means as time changes, the voltage is likely increases and again it will decreases and falls to 0. That means we get the maximum value and 0 value. Again maximum, again 0. But the purpose of the rectifier is to conversion from AC to DC. So DC is the direct current. That means only the current which is constant value, right? So for that here it is V and here we have D, means we get this one as the direct voltage, right? So this voltage we call as DC voltage, right? So but here we are getting the pulsating voltage in the half sinusoidal forms. So we need to change this form into straight line, right? So for that purpose we are adding the filter. Right? So by using the filter, we are changing the pulsating voltage into the constant voltage. So that one we call as filter. So by using the filter, we are converting the pulsating voltages into the constant voltage. Right? So what is filter and how it will be worked? Right? For that. Considering this one as the experimental setup, this one is considered as rectifier. It has input AC here, that is AC source. So from here we are getting in the two terminals, that is X and Y. So we have one load resistance, right? So across this load resistance, we are getting the output. Calling this one as XY. So this one. AB, right? So this is the load resistance. From here we are getting the output. So this one is the block diagram of the full wave rectifier, right? So this one is the rectifier. It consists of primary coil and the secondary coil and two diodes, right? So here we are getting the output is in the form of pulsating voltages. That means the values are increases and decreases, but the voltage is in the same direction. We need to change this pulsating voltages into the constant voltage. So that one is the process of the rectifier. So rectifier is converting from this alternating voltage in the form of the direct voltage. That means it has the constant voltage values. So for that we using the filter, right? Filter is nothing but by connecting a capacitor which is in parallel to the load resistance, right? So this one is the capacitor having capacitance C, which is connected in parallel with the load resistance, or we can connect, this is the load resistance or L, we can connect the inductor of inductance L in series with the load resistance. So either we can use the capacitor or we can use the inductor. So this one we use the, so this is the filter. Filter is nothing but adding the capacitor of suitable capacitance in parallel with the load resistance, right? So this one is filter, right? So in filter we can use either capacitance or we use the inductance, right? So capacitance, if we use capacitance means, so this capacitance must be added in parallel with the series resistor, that is load resistance, or if we use the inductance means we need to add that inductance in series with the load resistance, right? So here what happens, as the output voltage comes out from the rectifier and it flows across the capacitor and it gets fully charged when there is no load resistance. So this capacitor is fully charged, right? So after that fully charged, this capacitor will lose the charges during the negative half cycle, then it flows the charges from capacitor to the load resistance, that is when it is connected with the capacitor, right? So it will loses its charges during the negative half cycle, and again when the positive voltage will comes, again this capacitor is gets charged, right? So during negative half cycle again it will loses its charges to the load resistance, that means it has to maintain the constant voltage, right? So for that it start from here, this is during the positive half cycle, and as the voltage goes on decreasing, right? So that voltage has to given by this capacitor, that means it loses its charges, that means it gives the charges to the load resistance, right? So that time what happens, we are getting like this. So this capacitor is balancing the voltage of the load resistance, right? So during negative half cycle, once again it will send its charges to the load resistance, right? So here is the load resistance, it sends its charges to the load resistance, that is during the negative half cycle. Again positive half cycle, this capacitor is completely charged and it loses its charges to the load resistance. So this process will continue like this, right? So from this we can eliminate this value, that is the decreasing of the voltage is removed by using the capacitor, right? So that one we call as the filter, right? So we getting the current which is constant current, so this current we call as direct current, that is DC current, that is we are converting from pulsating voltage into the DC voltage, that is direct voltage or direct current. So by using the capacitor which is connected in parallel to the load resistance, so that one we call as the filter. So how much percentage, that is how much this capacitance work means, if we use the capacitor that has larger capacitance means it gives the more number of charges to the load resistance, then only we get the constant term. That means in the filter we uses the large capacitor and the time constant. So here along x-axis we have time, right? So there is a time to decrease and there is a time to increase. So we need to maintain that time to get the constant voltage, right? So this is the inverse product of the capacitance. So that is the inverse product of the capacitance and the load resistance RL. So that time we call as time constant. So for this particular time constant, we are getting the constant voltages, right? So from that we get a direct voltage in the form of the straight line. That is how we can convert the pulsating voltage into the direct voltage means by using the filter. So how filter work means, so filter is connected a capacitor in parallel with load resistance RL, right? Or we can connect inductor in series with load resistance RL. So this one is in series when we connected the inductor, or we can connect the capacitor in parallel with the load resistance RL, right? So this is the advantage of the filter, right? So the main purpose of the capacitor we connected for the load resistance is to it balances the charges, that is which stored while the output voltage is coming, that is during positive half cycle this capacitor is completely charged. During negative half cycle it loses its charges to the load resistance RL. From this we get the constant output voltage. So there is balancing of the voltage, right? So this is the filter. From this filter we converted the pulsating voltage into the DC voltage, right? So this is about the full wave rectifier, right? So next is, so half wave rectifier and full wave rectifiers are the devices. So which devices are those? Those are the semiconductor devices, right? So next, special type of semiconductor devices. So that is special type of PN junction diode. So one is the special type of the PN junction diode. So that one we call as Zener diode. So after the scientist invented this diode, his name is Zener, hence the diode name is given. That one is the Zener diode. So Zener diode is a special type of the PN junction diode. So that means diode consists of two types of the semiconductors. One is P-type semiconductor and another one is N-type semiconductor. So what is the difference to the common diode to that of the Zener diode is, so Zener diode is constructed to work only under the reverse biased condition. That is under reverse bias condition in breakdown voltage. So what is Xenon diode? So Xenon diode is a special type of the PN junction diode. So it is constructed to work under. So it is constructed to work under reverse biased condition. So only this diode will work under in the reverse biased condition, that is in the region, that is in breakdown voltage region, right? So the purpose of the voltage, that is purpose of the Xenon diode is used to in the application of voltage regulator, right? So in voltage regulator we are going to use the Zener diode, right? So how we constructed the Zener diode? As we know, the diode is made up of the two junctions, that is P-type junction and N-type junction. So in between the P-N junction we have the depletion layer, right? So this depletion layer consists of the minus negative charges and positive charges. So and there is an electric field in between the region, that is from positive charge to negative charge. So this is all about the diode, right? So how the Zener diode is constructed? So Zener diode is constructed to the, so this one is the diode, so heavily doped PN junction. So doping is more, that is heavily doped P and N region. So if we consider this one as the diode, right, electric field is more. That means E is more. So electric field is more is nothing but the force between the charges. Here negative charge and positive charge is more. Due to this strong electric field, so it has a tendency to gives the force to the valence electron that has to shift from the valence band to the conduction band. So due to this electric field, so there is a more chances of shifting valence electrons from, right. So this is the energy levels, right? So this one is the valence band, and here we have this is the valence band, and here is the conduction band. So as the electric field is more, because the thin depletion layer, as the electric field is more, so more number of the electrons are shifted from valence band to the conduction band. So if we have more number of the electrons in the conduction band, that means flow of current is more. That means more number of electrons which are available for the conduction. So that is in the electric field we applying in here. That means the electric field which is generated in the depletion layer, it breaks the covalent bond because electric field is more. So if it breaks the covalent bond, then more number of the electrons which present in this valence region, that is in the N region, is easily shifted to the P region. Right, so more number of the electrons are passing because this layer is very thin. So it acts as a wall between the two, P and N. So if the thickness is more, then penetration of the electrons or holes from either side is very less. So if this thin layer, here the electrons which are present in the N type, because in N type the electrons are the majority charge carriers, right? So it is bonded with the covalent bonds. Due to this electric field, the electrons covalent bonds are gets into breakup, and hence more number of the electrons are passing. So as the electrons is more number available in the conduction band, then more current is flowing in the external circuit, right? So if you plot the graph, that is IV characteristics for the Zener diode. So this one is I and this one is the V. So as the Zener diode is worked only under the reverse biased condition, so as we apply the reverse voltage, so initially it has very less current. For a particular current, we getting the maximum current. So that voltage we call as, that is breakdown voltage, that is DR, right? So for a small change in the current, that is small change in the voltage, we getting the maximum current, right? So from here to here we are applying the voltage, right? So but current is less. For example, here we are applying 0.2 volt. So here we have 0.4, here we have 0.6, and here we have 0.8 volt, right? So as we increasing the voltage, but there is no change in current. So if you observe here, the current value is very less. That is almost to the zero values. So when it reaches the breakdown voltage, the current value is suddenly increases. That means here we have the current I, right? So for the lesser voltage, we are getting the maximum current. So if here it is 60 microamperes, then for the small voltage, we are getting the maximum current, right? So that is the principle of working of the Zener diode. So what is the principle of the Zener diode? Means when the voltage, that is reverse biased applied voltage, is almost equal to the breakdown voltage, then current is suddenly increases. That means, so we getting the constant, that is increasing current for a constant voltage, right? So if you observe here, the breakdown voltage, if we taken this one as 0.8 volt, then for 0.8 volt we have the current here is 20 microampere. For the same 0.8 voltage, we have the current is 40 microamperes. right? So for the same voltage we are getting 60. That means voltage remains constant, but current values what happening? So current values goes on increasing. That means for the constant voltage we are getting the increasing current. So this one is the principle behind the Zener diode, right? So what is Xenon diode? So Xenon diode is a special type of a diode, so which is working under the reverse biased condition, right? So it is used in the voltage regulator. So the purpose, that is application of the Xenon diode is the voltage regulator, right? The principle is when the applied voltage, that is reverse bias voltage, is almost equal to the breakdown voltage, then we are getting the increasing current. That means for a small increase in voltage, we are getting the large number of the current, or we can say for a constant increasing current in a applied voltage, right? So the symbol of the Zener diode is almost similar to the normal diode, right? So here we have one. So this is like this. So this is the symbol of the Zener diode. So here it is B and here it is N. So this is always working under the reverse bias condition. And if you plot the IV characteristics, so this is also important. Here it is B, here it is I. So this should be a straight line, right? So this voltage is VR voltage. Right. So graph, and this one is the symbol and Zener diode. So application of the Zener diode is what? That is voltage regulator. Right. So how voltage regulator works? So the output voltage as we get in the rectifier. So in the previous we discussed about the rectifier, that is the output voltage which is comes out from the rectifier. So that output voltage is connected to the diode, that is Zener diode, along in series with the diode. It should be a reverse biased, because it works only under the reverse bias. So if we connect this one in the forward bias mode, then there will be no reading across the voltage and current. This one is current, right? I, and here this one is V. So this is the unregulated voltage. That means input voltage. So this is comes from the output of the rectifier, right? So this one is the resistance which is connected in series with the Zener diode. It is P region and it is N region, right? So now the output regulated voltage can taken from the load resistance which is connected in parallel with the Zener diode. So this one is the load resistance RL, right? So here we getting the output, that is regulated voltage, right? So this one is the setup of the voltage regulator, right? So what happens in voltage regulator? So this is working under the principle of, as already says, that when applied reverse bias voltage is equals to breakdown voltage, right? So what happens when the applied reverse bias voltage is equals to the breakdown voltage for a small change in voltage, large current is obtained. So this one is the principle. So principle of the Zener diode is when the applied reverse bias voltage is equals to the breakdown voltage, then that is V is equals to VBR. Then for a small change in applied voltage, so this voltage is the applied voltage. For a small change in applied voltage, we are getting the large current. That means here we getting the straight line. That means when V is equals to V bar, we get VBR, we getting the large current, right? So by this principle, so this voltage regulator is working, right? So when unregulated voltage which is comes out from the output of the rectifier which pass through the diode that is connected with the series resistance, right? So as here the current which is flowing, that means it should be reverse bias. Reverse bias nothing but this P junction is connected to the negative terminal and N junction should be connected to the positive terminal, right? So then here the applied voltage here is positive and here the applied voltage here should be the negative, right? So plus and here is minus, then again here we getting minus and here we getting plus. That means this Zener diode acts as reverse bias, right? So now as current increases in the circuit, right? So as current increases, the voltage drop across the resistance in series also increases, right? So here the current is increases. For example, the current initially I is equals to some 2 ampere. So this resistance is constant. For taken this resistance is 1 ohm, right? So we need to find the voltage drop across this resistance as from the Ohm's law V is equals to I into R. So here current is how much? 2 ampere and the resistance RS, it is how much? That is 1 ohm. So we are getting the voltage 2 volt, that is across the resistance, right? So as the current increases, right? So here the flowing of the current is equals to the flow of the current across the Zener diode, right? So if 2 amperes is flowing in this circuit means across Zener diode also the flow of current is 2 amperes, right? So now if we increase the current from I is equals to from 2 amperes to 5 amperes, that means voltage is increasing, that means current also increasing. So as current increases, the voltage across this resistance is how much? So current becomes, here it is 5 into 1, that means 5 volt. So if you observe here in the initial current is 2 ampere, we are getting 2 volt. When current is 5 ampere, we are getting 5 volt. That means as current increases, so in the same manner voltage also increases across the resistance which is connected in series, right? So as current increases in the circuit, so current increases in the Zener diode also, right? Next, so here as current increases, the voltage drop across the resistance also increases, but here the voltage drop across this Zener diode remains constant. That means we are getting the regulated voltage, right? So for example, here across this load resistance, because these two are in parallel, so here we have some 5 volt means across this load resistance also 5 volt, right? So understanding this one, so the potential or the voltage across any conductor or any diode which is parallel with the voltage, then both those two are of the same voltages, right? So here 5 volt means here also 5 volt, right? So now the Zener diode, as we increases this current, when increasing in current nothing but increasing in voltage, as this voltage reaches the breakdown voltage, right? BR, that is for some particular current, right? So here the breakdown voltage, if we taken, that is some 0.4 volt. So this voltage is the breakdown voltage of this diode. Next, if we increase the current, the voltage across this diode remains same, right? So if you observe here, if this BR voltage is 0.4, now we are going to increase the current. So here it is 10 ampere, 20, 30, 40, 50, right? So if we increase this current from 20 to 50, so is there any changes in the breakdown voltage? No, there is no change in the breakdown voltage. That means as we increases the current, the voltage across this diode remains same. Right, so as this current, that is voltage across this diode is same, then voltage across this load resistance is also same. That means we are getting the constant voltage across the output. That means we getting the regulated voltage, right? So here we are applying the variable voltage, right? So but here we are getting the constant regulated voltage. Hence the device we call as voltage regulator, right? So as we increases the current in the circuit, so the current is increases in the series resistance and also in the diode, but the voltage is increases in the series resistance but not in the diode. So as this diode has the constant voltage, that is breakdown voltage, so same voltage will be across the load resistance RL, then we getting the output, that is the regulated voltage, right? So this is the working of the voltage regulator, so which is based on the principle of the Zener diode, right? So this is about the voltage regulator. So important here is circuit diagram plus graph and the principle of the Zener diode, right? So this is also in the lab. So you can get the values in the lab experiment, then you can clearly understand the theory what we are discussed here, right? So in the next class we will discuss with some other types of diode, right? Thank you.